When I first encountered the concept of Jinping, my imagination was literally blown away by the scale of engineering genius. Imagine a dam located on the Yalong River in Sichuan province, erected so that its height is in yards. It's as if 195-story buildings were stacked one on top of the other in front of you, creating an incredible vertical wall. Over 9 years, from 2005 to 2014, hundreds of engineers and thousands of workers poured millions of cubic yards of concrete into this structure. So much that if it were spread out, it would be comparable to building 45,000 regular houses. This massive arch structure is not just a set of numbers, figures. Every inch of the dam was calculated with utmost precision, as if an artist sculpted their masterpiece statue, where each facet is responsible for distributing the enormous hydrostatic pressure. Jinping 1 was designed to withstand powerful floods, acting as a protective shield for thousands of hectares of farmland and millions of homes. The spillway system built into the structure activates instantly with a sudden rise in water level, like a giant umbrella ready to take the brunt of the elements. Special attention was also given to the social aspect of the project. More than 1,000 residents were relocated to make space for the construction of this giant dam. A sacrifice comparable to the loss of an entire small town, but necessary to ensure the safety of millions of people. This sacrifice became a vivid example of how human ingenuity can harness nature, turning its destructive force into a source of reliable clean energy. Every time I think of Jinping 1, an image comes to mind where concrete and steel, like in a giant construction set, come together to form a monument capable of changing the fate of an entire region. It's not just an engineering structure, it's a symbol of triumph, of precise calculations, and modern technologies, where every detail plays its vital role. Immerse yourself in a world where every centimeter of the structure matters, and engineering calculations are comparable to the work of watchmakers creating a perfect mechanism. Take, for example, the Hoover Dam, a true symbol of American engineering. During its construction, engineers decided to leave the central gap exactly 5.906 feet, which can be compared to the width of a standard door. This gap allows the concrete to contract freely during curing, preventing cracks that could collapse the entire structure, much like a carelessly built Lego tower. To manage the river's turbulent flows, engineers redirected the water through 4 gigantic tunnels, each of which can be compared in size to a massive underground corridor in an ancient castle. Temporary dams made of crushed stones, created at the construction site, allowed the area to be drained, as if someone temporarily shut off the water supply to make repairs. The pipes. During the construction process, drilling rigs were used, with 30 drills operating simultaneously, reminiscent of a symphony orchestra where each note is a hammer strike on the rock. After blasting the rock mass, excavators immediately began clearing the debris, while rebar frameworks and hydraulic formwork secured the tunnels, turning them into reliable channels for regulating the water flow. The spillway system built into the dam allows for the immediate release of excess water, like a powerful valve protecting the structure from overloads. This complex of engineering solutions requires constant monitoring, and every element is meticulously planned, from the choice of materials to the optimal angle of the structure's slope. For me, this is not just a construction process, but a true triumph of human intellect over the elements. Here, every detail is the result of years of research and testing, every technology. The key to turning risk into stability. And when I observe how these gigantic structures, like living organisms, function under conditions of extreme humidity, temperature fluctuations, and unstable ground, I realize that engineering mastery is an art where science meets practice, and every decision becomes a guarantee of safety for millions of people. In the world of dam engineering, solutions are so diverse that parallels can be drawn with natural landscapes. Each structure is unique, like an individual ecosystem biome, where different materials and technologies are used to combat the force of water. Let's start with gravity dams, gigantic structures where the main support is created by the enormous mass of concrete. Imagine that the thickness of the base of such a dam can reach sizes comparable to the height of a large skyscraper. Their stability is ensured solely by their own weight, like a massive boulder that does not yield to the pressure of the elements. Arch dams represent a more elegant engineering solution. Their shape allows for the even distribution of water pressure across the entire arch, reminiscent of an ancient arch in a temple. Such dams rely on natural rock formations, which allows for minimizing material costs while maintaining high structural strength. This approach requires incredible precision in calculations. One mistake, and the balance can be disrupted like a collapsing bridge. Earthen embankments are dams that seem to grow out of the ground itself. They consist of thousands of cubic meters of compacted soil, mixed with clay for waterproofing. Imagine a huge mountain, shaped by the hands of engineers, where each layer is compacted to the limit. Such structures adapt well to various types of terrain, although they require regular maintenance to prevent erosion. Rockfill dams. Another type, where massive stone blocks, laid with millimeter precision, form an impermeable barrier to water. These structures are as if someone laid them out with huge boulders. The wall is capable of withstanding even the strongest onslaughts of hydrostatic pressure. Each of these dams has its own advantages and disadvantages. Gravity dams provide high reliability due to their mass, while arch dams allow for material savings. Earth and rockfill structures are flexible and adapting to complex landscape conditions. I am amazed at how engineering ingenuity finds a solution for every challenge. Here, technology and mathematics intertwine with practical experience to create structures that not only protect us from the destructive force of water but also provide clean energy. These engineering masterpieces are not just objects. They are living systems that daily maintain the balance between the power of nature and human intellect, turning risk into a source of stability and development. When it comes to the most dangerous dams, structures immediately come to mind whose reliability is constantly tested by extreme natural conditions and human factors. At the top of this list is the Banqiao Dam in China. Built for flood control, it gained a tragic notoriety in 1970, when heavy rains led to its collapse. The scale of the tragedy was colossal. The death of over 170,000 people demonstrated how fragile even the most massive engineering structures can be. Here, every calculation error, every discrepancy in construction could be fatal. Constant maintenance and upgrades remain necessary to prevent a repeat of such a catastrophe. The second item on this list is the Mosul Dam in Iraq. Located on the Tigris River, it is built on an unstable gypsum foundation. This creates a constant threat of collapse. The unstable ground requires regular inspections and costly repairs. Each seasonal cycle of rains can exacerbate the problem, and even a small change in hydrostatic pressure can cause cracks in the structure. This makes the Mosul Dam one of the most dangerous, as any breach of integrity could lead to the flooding of the nearby city, which has a population of hundreds of thousands. In third places, the Oroville Dam in the United States of America. Despite being the tallest dam in the country, in 2017, heavy rains almost caused it to collapse. A failure in the spillway system forced a massive evacuation, and the situation could have turned into a real catastrophe for large areas of California. The technical systems responsible for regulating the water flow proved to be insufficiently effective under the conditions of an extreme increase in water levels. This forced engineers to reconsider their approaches to spillway design. By implementing new sensors and automated control systems capable of responding more quickly to changes. These examples demonstrate that dam safety is an ongoing process, requiring not only initial quality design but also regular maintenance, upgrades, and a clear monitoring system. Each of these structures is not just a massive construction, but a complex engineering system capable of either sustaining life for millions of people, or, with the slightest malfunction, turn into a large-scale tragedy. That is why the latest technologies are used to ensure safety, allowing for the prediction of changes in the structure and timely warning of potential risks. Engineering is always about precision and responsibility. In the case of dams, any error in calculations can lead to disaster, and every detail plays a crucial role. This applies not only to hydraulic structures but to any engineering projects, from residential houses to industrial buildings. That's why it's so important to trust construction to professionals. And if you want your project to be thought out to the smallest detail and executed with impeccable precision, turn to the professionals at the Production Association System. This is a leading manufacturing enterprise with a full range of services. From designing modular buildings and houses for various purposes, of any complexity, to developing design projects, including interior finishing. The team provides a guarantee for their work, which is very important in our time. Large-scale dams are the embodiment of engineering grandeur, capable of transforming entire regions and impacting the economies of countries. At the forefront of this indicator is the Three Gorges project in China. It is the largest dam in the world, built on the Yangtze River. Its volume is approximately 31,650,000,000 acre-feet of water, which can be compared to a volume sufficient to supply a large metropolis with water for decades. This dam plays a key role in flood control. It generates electricity and improves navigation on the river, making it a strategically important facility for the entire country. In second place is the Itaipu Dam, located on the border of Brazil and Paraguay. This giant is not only the second largest hydroelectric power station in the world but also one of the most important energy facilities for both countries. Its volume reaches approximately 10,156,000 acre-feet of water. The dam provides stable energy supply, which is critically important for the industrial development of the region, and also promotes interstate cooperation in the energy sector. The third place in the ranking belongs to the Zilote Dam, built in China on the Jinsha River. Its volume is approximately 10,246,000,000 acre-feet of water, allowing it to compete with the world's largest hydroelectric power stations. This facility demonstrates high efficiency in production, in terms of energy generation and water flow management, which is the result of advanced engineering calculations and the latest construction technologies. All these dams do not just play the role of water balance regulators. They represent highly complex engineering systems integrated into the economic and social infrastructure of their regions. Each of these projects required massive investments, meticulous work by engineers, and modern technologies. The use of innovative materials, advanced control systems, and automated programs for monitoring the condition of the structures significantly enhances the reliability of these facilities and reduces the risk of disasters. These gigantic dams are an integral part of the modern world. They provide electricity to millions of homes, contribute to the development of agriculture and the transportation system. Their scale and efficiency demonstrate how technology can transform nature into a source of prosperity, despite the constant challenges posed by the elements. The most complex engineering tasks require precision, innovation, and years of experience, and the dams included in this ranking are a vivid example of that. The first place here is occupied by the Hoover Dam in the United States of America. This structure is known for its gigantic central gap, which allows the concrete to freely contract during curing. Such technology prevents the formation of cracks, ensuring the durability of the structure even under colossal water pressure. Every element of the Hoover Dam is designed with extreme weather conditions in mind, making it a symbol of advanced engineering thought. The second most complex project is the Three Gorges in China. Its construction required the redirection of an entire river through 4 specially dug tunnels, which in itself is no simple task. Temporary dams made of crushed stones allowed the area to be drained and created conditions for safe construction of the main structure. Such an approach requires not only precise calculations but also high-tech equipment capable of operating in extreme conditions. Each stage of construction was accompanied by constant monitoring of soil conditions and hydrostatic control, making this project one of the most complex in the world. The third place in this ranking is occupied by the dam in Itaipu on the border of Brazil and Paraguay. Its construction required the use of the most complex engineering calculations to manage the powerful flows of the Parana River. Control over hydrostatic pressure, selection of optimal materials, and precise organization of work. All of this became the key to the successful completion of the project. The use of advanced technologies and continuous improvement. The construction methods allowed for the creation of a structure capable of withstanding extreme loads and ensuring stable electricity production. These projects demonstrate how complex engineering can be. When it comes to creating structures capable of withstanding the elements, each one is the result of the coordinated work of many specialists using innovative technologies and scientific achievements to achieve maximum reliability. From the development of unique spillway systems to the implementation of automated monitoring systems, all these solutions are aimed at minimizing risk and ensuring the longevity of the structure. The most complex dams are not just engineering structures, but living systems that require constant attention and updates. Their reliability depends on every detail, from accurate calculations to timely maintenance. These projects demonstrate how modern technologies and deep knowledge in the field. Hydraulic engineering can transform risk into a source of stability and progress for millions of people. When it comes to the beauty of engineering creativity, one cannot overlook dams that combine functionality with aesthetic perfection. One of the striking examples is the Hoover Dam in the United States of America. Its arch design, created with complex calculations of hydrostatic pressure distribution, demonstrates the sophistication of engineering design. Here, Every detail from the meticulously designed central gap to the even distribution of loads throughout the structure testifies to how science and technology can create not only a reliable but also a visually appealing structure. Thanks to high-precision technologies and the use of modern materials, the Hoover Dam remains a model of durability and stability, despite the impact of extreme weather conditions. Another example of the beauty of engineering solutions is the Kariba Dam, located on the border of Zambia and Zimbabwe. Its structure is made of strong concrete with a double curvature, designed to maximize the efficient distribution of the water forces acting on its surface. Technical calculations and precision in assembly allowed this dam not only to perform tasks of flow regulation and electricity generation, but also to create a harmonious silhouette in the landscape. Kariba demonstrates how well thought out combination of functional elements and thoughtful design can turn an engineering structure into a true symbol of stability and beauty. No less impressive is the Glen Canyon Dam in the USA. Its design was developed with a focus on durability and safety, achieved through the use of innovative technologies and meticulous control. The quality of materials. Externally, the Glen Canyon Dam looks understated, but its technical features, complex spillway system, integrated pressure control sensors, and automated monitoring systems make it a model of modern engineering art. This dam demonstrates that beauty doesn't always have to shout with bright colors. Sometimes it is expressed in perfect proportion, precision, and reliability. These dams are not just infrastructure objects, but the result of years of research, engineering expertise, and innovation. They show that it is possible to achieve a harmonious balance between strict technical requirements and aesthetic perfection. Engineers, when creating such structures, do not sacrifice functionality for appearance. They bring to life projects capable of serving for centuries, remaining a symbol of human intellect and creative approach. Each of these structures is proof that technology can be not only useful but also beautiful, combining functionality, safety, and aesthetic appeal. Today, global engineering thought is actively seeking ways to integrate environmental requirements with traditional tasks of controlling water flows. The latest dump projects are focused not only on increasing the efficiency of electricity generation and flood control, but also on minimizing environmental impact. In several countries, innovative projects are already being implemented where technologies are integrated to preserve natural fish migration routes and ensure natural water circulation. For example, in Norway, work is underway to create dams equipped with special fish passage mechanisms. These devices consist of tunnel and lock systems designed to allow free movement of fish between water basins. Precise engineering calculations and hydrodynamic modeling enable achieving an optimal balance between the structural strength and its environmental safety. As a result, such dams not only fulfill the tasks of generating electricity but also contribute to preserving biodiversity in the region. In the Netherlands, movable dams are actively being developed, capable of automatically regulating water levels during storms. These structures are equipped with sensors that monitor the dynamics of water flow, and automated systems that, in the event of a sudden rise in water level, open the locks to release the excess volume. This approach reduces the risk of dam destruction and minimizes flood damage while preserving the natural features of the riverbed. The use of innovative materials and adaptive technologies makes these projects a model of synergy between engineering and ecology. Moreover, modern projects focus on energy efficiency. The latest materials used in dam construction have improved thermal insulation and waterproofing properties, which help reduce energy loss and lessen environmental impact. Combined with monitoring systems that track the condition of the structure in real time, such dams provide increased reliability and durability. Effective water resource management becomes possible through the integration of modern information technologies, analytical systems, and automated solutions. Thus, the dams of the future represent a harmonious blend of engineering expertise and environmental responsibility. Innovative approaches not only enhance the efficiency of traditional dam functions but also create conditions for preserving natural ecosystems, ensuring sustainable regional development. These projects demonstrate that modern engineering can keep pace with nature, minimizing negative impacts and opening new opportunities for the use of water resources to the maximum benefit of society. In conclusion, it is important to note that dams, they are not only engineering structures but also complex systems that require fine-tuning to ensure safety and efficiency. Modern technologies allow for the creation of structures capable of withstanding colossal loads, while maintaining ecological balance. Engineers today use advanced calculation methods, automated monitoring systems, and innovative materials so that each dam can adapt to changing conditions and minimize environmental impact. Every structure, whether it's a giant dam on the Yangtze River or an innovative dam with fish passage mechanisms. In Norway, it is the result of years of work and scientific research. During the design and construction process, engineers faced the necessity of considering all possible risks, from extreme weather conditions to seismic activity and impacts on the biosphere. Regular maintenance, upgrades, and the use of predictive analysis systems allow for timely detection of deviations in the structure's condition and prevention of potential disasters. The balance between progress and nature. This is not just an abstract concept, but a practical task solved based on precise data and years of experience. Nature sets high demands on human craftsmanship, and each new project becomes a test where the safety of millions of people and the preservation of ecological harmony are at stake. In this struggle, innovation and engineering thinking play a crucial role, turning risk into a source of stability and development. Ultimately, dams symbolize our ability to adapt and utilize resources to the fullest benefit, while not forgetting the need for careful treatment of the environment. They remind us that even in a world of high technology, it is important to maintain a balance between human progress and nature, ensuring sustainability and safety for future generations. This is the true achievement of modern engineering, where every detail matters, and every innovation is a step towards the future, towards harmonious coexistence with nature.